Good morning. Here we are yet again for another lovely session of CENG 3325 Structural Analysis. This is going to be the 5th lecture. Today, we are going to be looking at trusses. So I have a few things I want to cover here as an introduction to trusses and an introduction to truss theory, etc. They are as follows. So I want to go down a list of topics, the things to know about trusses. So the first things I want to talk about are just sort of a list of topics. So trusses. Truss topics. And so what do we want to know about trusses? Well, first thing we need to know what a truss is, truss theory. So I want to define the truss member. What that means, what it means for something to be a truss member, what the significance is, etc. Oh, truss has 2 S's, not 3. 2, I want to look at types of trusses, or at least just truss theory in general. Truss theory, including determinacy. Then we want to look at ways to find member forces, including the method of joints, and for the method of sections. And these are going to be the 4 major topics that we learn in regards to trusses. So we have truss. First, we want to look at what a truss member is. Then we look at. Then we want to look at trusses from the broader point of view, including things like determinacy. Then we want to look at the method of joints, and finally the method of sections. Okay. So let's begin. First thing I want to discuss is truss members. What does it mean for something to be a truss member? And I'm going to bring this back to our discussion of members and member internal forces. So truss members are defined by their particular end support conditions. Truss members are defined by end conditions. By end conditions. And in physics and math, we refer to these as boundary conditions. You may remember that term from differential equations and from physics courses. Boundary conditions. We're going to use those terms a lot, or that term a lot in this course, aka boundary conditions. So what kind of boundary conditions can exist for a member? So let's look at some member boundary conditions, possible member boundary conditions. Member boundary conditions. Well, the ways we can support a member are virtually unlimited, especially if we start considering things with more than 2 support points. But in terms of members that have only 2 support points, we have the following possibilities. Well, we could have something like we could try a roller and a roller or something like that, but that's not going to be stable. In terms of something that actually be stable, what could we have? Well, we could have something like a pin-pin. We could have a pin-pin. We could have a pin fixed or a fixed pin. Pin fix. Pin fixed. Or we could have a fixed fixed. And we could also have a cantilevered member for something that's supported by on only one end. But these are the 3 ways, primary ways, or at least stable ways to support a member with 2 end supports. So these are the 3 stable ways to support a member via 2 end supports. Or I should just say via end supports. Now we'll look more at this one and this one later in the semester. Maybe I should show this like this here and this here. We'll look at these more later in the semester. But we're going to look at this one with trusses. So a truss is this particular one here. Trusses are made of pin members. So a truss member is one supported on both ends by pins. A truss member is one that is supported on both ends of it by pins. And at first, if you're not familiar with the theory of trusses, that may not seem that substantial. You might say, okay, well, what's the big deal? It's got pins on the end. Okay, that's nice. But what's important about it? Why is it important? What happens when a member has a pin support on both ends? And the key there is that, again, it all comes down to the end conditions. When you do that, something very special happens. And I'll go through this sort of short, rough and dirty derivation on the next slide. Okay, so let's look at the pin end support condition. The pin support condition. So if you have a member that has a pin support, so I'm going to draw this like this to illustrate that this doesn't have to be just a single beam, but these could be internal joints as well. So I'm going to draw like this, here and here, pin. Now, what is the significance of a pin? Well, the significance of a pin, let me call these ends A and ends B, or end A and end B. Let's say end A and end B. So what is the significance of an internal pin? Well, I know that at the end of that pin, there must be no moment. In terms of internal forces, if I apply a downward load like this to the center of the beam, or to the center of this beam, I would have bending here. But as long as there's no forces applied in the middle of the beam, there cannot be any moment at the even if there is a force in the middle of the beam, there cannot be any moment at the end, because there can be moment in the middle if I have a force in the middle, but anywhere along the end, at the end, if I could do a cut right at the end, there cannot be any moment. A pin support cannot support any moment at the end, or cannot resist any moment. I know that a pin support cannot resist moment. So there will be only, at the ends, there can be only axial and shear. However, when we put two pins together, we'll see that this collapses even further. Can be only axial and shear inside a member. If a member ends at a pin, or I should just say only axial force and shear. Or in terms of reaction forces, this would be a AX and an AY, a BX and a BY, a BX and a BY here. So if I didn't know anything about trusses, if I didn't know anything about truss theory, about anything else, I would say that just based on the pin support condition alone, there would be an AX, an AY, a BX, and a BY. Now, something else important about truss members, I'm going to assume for truss members, for trusses, assume that all forces are applied at joints. So we're going to assume that all the forces are applied at the joints. And we do that, that means that I can have force here or force here. I can push or pull any direction I want at that support, but I'm not going to have any loads inside of this. So now, so I'm not going to have any loads anywhere from A to B in this beam here, or in this member here. And when I do that, something special happens. So let's work through some equations of equilibrium and see what happens. So let's bring back our statics and run through some equations of equilibrium. So the first thing I'm going to do is try sum of moments about A. Sum of moments about A, counterclockwise positive. And if I look at this, let me go ahead and say this thing has length L, for example. It's going to make my math possible. So if I do a sum of moments about A, I see that my AX, my BX, and my AY, all of these have lines of action that pass through point A. What is the significance of that? There'll be no moment, of course. This is basic statics. So just know it's been a while since some of you had statics, so we're kind of starting slow and getting back into gear of things. So anyway, if I do a sum of moments about here, I will have, basically all I'll have is BY times L. And this is why it's important that I don't have any loads along the member here, because if I had a load along the member, then there'd be something to balance this. But because there's not, there'd be something to resist this B times L. But because there's not a load there, there's nothing to resist that. So if there's nothing to resist this, and I know for this to be in equilibrium, what does the sum of moments about A have to equal?
0.
Exactly, yes, if that's just basic statics. So BY times L has to equal 0, and so therefore, since L is definitely not equal to 0, I know that BY is equal to 0. BY must be equal to 0. I could do the same thing with the sum of moments about B. AX, BX, and BY all have lines of action that pass through point B. Therefore, they'll generate no moment. Therefore, I can say negative AY times L is equal to 0. And that leads us inexorably to AY being equal to 0. So both of our vertical forces here at the ends are equal to 0. Questions on that? Again, this is just basic statics. Now I have AX and BX here. So if I do a sum of forces in the x direction, I have no forces applied along the member, only at the joint. So therefore, I can say here that essentially I'll have AX plus BX is equal to 0. And that leads us to that AX is equal to negative BX. So in other words, the x force is are equal and opposite. The end axial forces, or the end x forces, are equal and opposite. Oh, nope, let's get out of there. Are equal and opposite. Equal and opposite, exclamation mark. Okay, so next I'll talk about what the significance of this is, this end support condition here in general. So I drew this. I want to talk about rotation of members. So what I proved previously was that if I have a truss member with pin-pin supports, or member with pin-pin supports, so it would be a truss member, I effectively have just two forces. That AX and AY, or AX and BX, can just collapse to a simple force P and force P. So a truss member we've already shown, a truss member will have only a single axial force applied at the ends. However, the derivation I did put the member right at the horizontal, and that did make the math a lot easier. So remember, I drew that member like this. I drew the member like this here, and that did make the math a lot easier. So that would be like an x axis, something like that, with it, or maybe just an y axis. So let's say I had an x-axis and a y-axis. But what if the member was at an angle? Would that change things? What if the member is at an angle? It would not change things, no. Now, it would make the derivation a little bit more difficult. So if I still had the x-axis and the y-axis here, at least if I insisted in staying in the x and y-axis, so you have an x-axis and a y-axis, and then let's say this thing is rotated an angle theta. If I insisted on still using the x and y axis, yes, that would make things a bit more difficult. I would have to run there. I could run through the same derivation. It would take a lot longer though, because there would be a bunch of sines and cosines in there, a bunch of sines and cosines of theta. But I can also see that by statics, if something is going to be in equilibrium, or for something to be in equilibrium, or as some pronounce it, perhaps somewhere, equilibrium, it must be in equilibrium about any and all sets of axes. Or I should probably say in equilibrium about any two perpendicular axes. If you chose non-perpendicular axis, that would be kind of weird, and I would have to think about where that would still hold true. Any two perpendicular axes. Perpendicular axis. So what that means is, for this member, there is no reason I can't just have, instead of a global x-axis, there's no reason I can't have an x prime axis and a y prime axis. There is no reason I can't do that. Now, if I had any loads that were given to me in terms of the x-axis and the y-axis, I would need to apply some trigonometry to get them into the x prime and y prime axis. If I had any lengths or geometries or things like that, I might have to convert them to the x prime, y prime axis. But again, for something to be in equilibrium, it has to be in equilibrium about any and all axes. So, this derivation here, this could be either in a global x-axis or it could be in an x prime axis. It doesn't matter. This derivation holds true regardless of your coordinate system. So it doesn't matter if the member is rotated, it doesn't matter what kind of angle it's at, it doesn't matter if I flip it around. A truss member, by nature of its supports, will only be able to support one axial force at the ends. Now, I might want to look forward and see how this relates external forces to internal forces. So let's look at truss members, external versus internal forces. Truss members, external versus internal forces. Let's look at truss external. Actually, I'll do that in green too. External versus internal forces. So maybe this would be obvious, but I do like that this is a good example of how we can relate external forces or boundary conditions to internal forces. So if I have a truss member, and I'm going to draw this thing as having some dimensions here for this slide. Usually I'm going to draw them as line items or line diagrams. But let's say I have a truss member. And I'll go ahead and show this with pin ends. Pin ends and pin ends. and there is a force P on either end. P and P. Basically, what I'm doing here is I proved before that AX equals BX, and then also that the BX has to be not really equal. The AX has to equal negative BX. In other words, they have to be equal and opposite. So I replaced those with a single axial force P, or we could call that F or something like that. In most of the derivations or most of the problems I'll solve going forward, I'll use like FAB to refer to the force on member AB or something like that. Now, let's do a cut on this thing and look at the member internal forces. This will connect back with what we've seen previously. We saw in sort of the first week. Let's cut this here and look at the member internal forces. So if I cut this, and note, of course, that even though this is drawn as as tension being applied to this, it could be, there are two ways to be equal and opposite. They either can both be pulling or they can both be pushing. So it can either be in tension or it can be in compression, either pure tension or pure compression. So if I have this truss member with a pin support here and a force P here and here, P, and then I have oh no, I forgot my internal forces. What kind of forces can exist in a member? Shear and moment. Anything else? I forgot. I just forget sometimes. Huh?
Normal.
Oh, normal or axial force. Yes, yeah. Sorry, I just forget sometimes. I'm just forgetful. So anyway, yeah, normal. Oh, it's called normal because it's always there, right? That's what normal force means, right? Oh no, it means normal because it's perpendicular to a surface. Yes, yes, yes. I'm just so forgetful. Anyway, then we have the shear force V, and then some sort of moment M. Okay, well, if I go ahead and do now if I do a sum of moments, I'm going to go ahead and call this, maybe I'll call this, I don't want to label my points with red because I try to reserve that for forces. So I'll call this end A, B, and let's say I cut this thing at X here. I'm going to cut this at some point X. So if I took a sum of moments about point X, this would not be ideal, or sorry, some moments about point A, this would not be ideal because the V and the M would both be present there. So I think instead, what I might do is I might start by maybe summing forces in the vertical direction. I think that'd be a good place to start. So if I sum forces in the Y direction, I get that V plus nothing equals 0. So therefore that V, or maybe that would be Vx or something, that Vx has to be equal to 0. Huh, interesting. That looks too much like an X. Sum of forces in the Y direction. Then I can do a sum of moments about, say, point X here. And I get M. Oh no, there's nothing else there. Who'd have thunk it? Plus M of X. And, that just equals 0. So mx equals 0. M at point X is equal to 0. Who knew? Or I could also call this V as a function of X equals 0. Questions? Oh, okay. Yeah, I'm just so forgetful sometimes. And then it's just, who'd have thunk it? And so anyway, then I can do the sum of forces in the X direction, and I have negative P plus N is equal to 0. And N then is equal to P. Huh. So therefore, I can see that the only internal force present in a truss member is that same axial force. This is why I like to look at trusses in structural analysis. It's a good way to connect back the idea of external forces versus internal forces. Is axial force. So we bring it back. Okay, questions on this?
Where did that VX come from?
That would be a v as a function of x here, basically. V as a function of x. Sorry, I'm being a little sloppy with my notation. That should be v as a function of x. Just cutting this at point x, essentially. We'll be using that when we do we'll be using that cutting it at a point x in our next lecture, or maybe the next lecture. I'll figure out the schedule. But when we deal with member internal forces and solving for member internal forces as a function of x, that's going to be real fun. Shear and bending functions as a function of x. Lovely. Okay, anyway, let's move on. And I want to look at, well, not quite move on. I have one more thing I want to talk about in terms of Truss theory. I want to remind us of our assumptions. Truss theory assumptions. And this is very important. So, everything, every kind of model, every kind of thing we do in engineering is going to have some engineering assumptions built into it. There's always going to be some assumptions. So the first one is the main one we discussed, is that there are pin members, and I should say there are ideal pins on both sides. A member is supported by ideal pins on both sides. This is, of course, completely impossible. There is no such thing as a perfect pin. There is no such thing as a perfect roller. There's no such thing as a perfectly fixed connection, because a perfectly fixed connection would be one that essentially you could apply no matter how much load you apply to it, it doesn't move at all. Or even the strongest of connection, if I just lean on it, will bend slightly. That connection will rotate ever so slightly. So there's no such thing as a fixed connection. There's no such thing as a pure pin connection. Everything is somewhere in between. But you know what? For how we connect up members, we've discussed that before. We've discussed what idealized pin versus a real pin, all that kind of stuff. I think we discussed that toward the beginning of the course. Then, what's next? Another thing we mentioned was that loads are only applied at the joints. So loads are only applied at the joints. This is also completely impossible. Why is this completely impossible? Weight, self-weight is always a big one, yeah. So this is what I like to do is I do like to come back and discuss the limitations of models. And so yes, we can draw it, even if we had a physical truss where, say, we only applied loads. For example, if this was a truss holding up some beams, like a bridge beam or something, so like you could have imagine you had a truss like this. Let me draw one out, like this. Maybe this is a truss for a major structural truss for a bridge or something. We could make it so the vast majority of the load was applied at the joints. So for example, we could have maybe there would be a road deck along here, and we could have beams going into the page, and we would hang those beams only from the joints. So we could make it so 99% of the load or 95% of the load or whatever it might be was applied at the joints. We could do that. And so that would make it a pretty decent assumption. But we know that we can never get that perfectly because, at least for something in a gravitational field, and everything is under a gravitational field, even something in space, because there's still, even if it's in orbit and the gravity of Earth is not having an effect because it's in free fall, I could still argue a technicality and say it would still be feeling the gravity of other planets or something like that. So anyway, but most things we're building in civil engineering applications are not in space. And so what we have to worry about is self-weight, and the self-weight of members are not distributed at the joints. They're gathered at the joints, but they are generated throughout the entire length of the member. They're always going to be gathered throughout the entire length of the member. So we know that this is completely impossible. And I don't feel the need to draw all of these, but it does give the impression. So that means that in Truss members, there is always going to be some moment in there. So if you are, now nowadays if you're designing bridges, you're going to use computer models and such, but if you're designing a bridge, a long time ago and using purely hand methods, the way you would do this is you would analyze the entire thing as a truss, but then you would design each individual truss member like a little beam. So you would make sure this member itself had enough bending capacity for its own self-weight or any loads that you apply to it, and then you would design the global loads, the global stability, based on a truss model. So, but anyway, so yes, so I'm coming back to these things are impossible, but just because an assumption or a model is impossible, doesn't mean that the idealized case cannot be useful for design. This is one of the reasons we do have things like factors of safety and LRFD and things like that. One of the reasons for that is to take into account the slight differences between our idealized model and the real world situation. But you need to make sure to use the correct model, because if you are using an incorrect model, your modest factors of safety won't take care of that. We might design things twice as strong as they need to be in some extreme cases, but we very rarely design things 10 times as strong as they need to be. So it's okay to use models, appropriate models to your condition, to your system, to your structure, but you need to know where that model is applicable, where the assumptions are valid, etc. Let's see, what else? Another big assumption is straight members. So I'm assuming that my members are perfectly straight lines. Lovely. Now, truth be told, usually steel members are straighter than I draw them on the page here. Here's a case where my hand drawings are actually, you would think something on paper would be straighter than something in the physical world, but not in this case. So, truth be told, yes, most steel members are, this would be, that would be a very, if someone brought one of those into the shop, you'd be, you wouldn't be hiring that contractor again, but that supplier again, that mill again. But anyway, so usually they are straight enough that you can't detect the curvature with the naked eye, but we know, again, that there is no such thing as a straight beam. Now, there actually are cases where you can see curvature in the members, especially if you have, if you go down to Home Depot or Lowe's and you go and buy some good old pine 2x4s or something, you can set those in the ground, and most of the time you'll see that they have a good bit of curvature in them, because those aren't made to be perfectly straight. They're made to be cheap. They don't. If you're just using this for wall studs or something, they don't need to be perfectly straight. They serve their function just fine. So, but in our models, we are assuming perfectly straight members. So, and let's discuss why. I do want to mention why that's important, because if I have a member, let's say I have a member that's not straight, that's bent off to the side of it. Let's say I have a member that even before any loads applied to it is kind of bent over a bit like that. Well, let's look what happens when I apply end forces to this. If I apply an end force to this, P and P, let's look at this, label this here. I would have a slight displacement here, and I might call that delta. And so what I have is, in structural engineering, when we talk about the combination of bending and axial force, this is referred to as the P delta effect. But anyway, what I have here is a P and a delta. Or in other words, what I have is, if I take moments about here, no longer does this not generate a moment, because now I have a moment. This thing will create a moment. This is point A, moment about A, some moments about A. Well, I will now have a P times delta. This force will now generate a moment because it's offset. If the member is curved at all, it's going to generate a moment, and that's going to mean if this thing is not perfectly aligned, that the end forces will generate a moment, and that means my assumption is no longer valid. And there's one other major assumption. We could talk about homogeneous and isometric materials, that sort of thing. I don't think that's going to be too important to this, because we're not really talking about stress and strain. Those will come into play later when we look more at virtual work and things like that. So what I would like to discuss, though, the final assumption I would like to look at would be centric loading. Maybe I'll do that on the next slide. I want to discuss on the next slide here, centric loading. the fourth assumption, the fourth key one that I think is the fourth assumption I think is key for trusses would be centric loading. Centric axial loading. So basically, we already know that the forces will be applied. Actually, I shouldn't say axial loading because that is determined by the truss condition, or the pin condition. That's guaranteeing that. But I should say centric loading. So when I say centric loading, I mean that the centroid of the load of the axial load is applied about the centroid of the member, or applied through the centroid of the member. Through the centroid of the member's section. Okay, so let's discuss this here. Now, imagine for a moment I had a, let's look at non-centric loading, or offset loading, or I should start eccentric loading. Let's look at centric loading versus eccentric loading. And centric loading. Now, I'm going to keep this simple by looking at, let's say that we have a member with a rectangular cross-section. So that'll be easier to demonstrate, I think. It'll be easier to demonstrate this with a rectangular cross-section. Maybe I'll make a nice big one, nice big diagram so we can see what's happening here. So first, I'm going to draw in one color. I'll draw the member area. So that's there's no surprises there. This whole thing is a solid cross-section, no surprises there. And since it's a rectangle, the centroid would be right in the middle. No surprises there. In fact, I probably don't even need the lines there. So the centroid of the member area would be right in the middle. And that would be true for both cases. Now, of course, we can have members that the centroids of their area are not right at the center, unless you're defining the centroid as the center. But for example, if you had something, like an angle or something like that, if you have a L shape, then the centroid of the thing is not even on the cross section itself. It's kind of in the middle, but it's kind of like if you have a L shape like this, the centroid is right there or something. But maybe you could call that the middle. But anyway, now in another color, I want to show the where the load would be applied. So when we draw things as point forces, we draw them as idealized forces where they're all acting through a single point. But we know that's completely impossible. I can't actually apply a force to a single point. Now, usually that's a decent assumption, especially if something is applied over a couple inches and we're looking at a member measured in many feet, a point load is a reasonable assumption. But we can't actually apply something to a true point load because if you could somehow apply something as a true point load, the pressure underneath that point load would be infinite. Pressure is force over area. If you applied something over zero area, the pressure would be infinite. So it's like, I don't know, setting a black hole on top of something. It would just fall through the earth. It would just go through any material like a stone through air or something. A true point load is impossible. It's another engineering model. So all real forces have to be applied over an area. So the force applied area. So with an eccentric loading, and it could be applied, it doesn't mean that it's only applied over a certain area. I'm going to show it as being applied only over part of the area for simplicity, or you could just as equally have it where it was applied over the entire thing, but maybe it was leaning more on one side than the other. But for simplicity's sake, I'm going to show it as being applied to only part of the member. So let's say we applied load to only part of the member, like I didn't connect this thing up right and proper, and so we were applying load to only part of the member. So the centroid here would be like this. This would be eccentric loading. The centroid of my load does not line up with the centroid of my member. Centric loading is like this. The centroid of my load lines up nice and close with the centroid of my member. They're going to be right on top of each other. So this is also completely impossible. I've been saying that a lot today. This is also completely impossible. The reason for that is you're never going to get everything to line up perfectly exact. You're never going to get the centroid to line of both of these things to land right on top of each other. But you know what? Again, for certain engineering problems, this is a perfectly valid assumption. If you do have members with pin joints, if you line things up proper, you know, if this thing is within a reasonably close distance, this is not going to be a factor. So what we're saying when you make these assumptions is we're saying that it's close enough to the center that we can consider it to be at the center. And those are the basic assumptions built into Truss theory. Okay, finally I might want to look at determinacy. Determinacy here. Truss determinacy. And I'll cover this second topic fairly briefly. So we mentioned that trusses are we've discussed truss members and those kinds of conditions. A ideal truss is one made entirely of truss members. So nothing but straight members on pin joints is one made entirely of truss members, and that makes sense. Now, that doesn't mean it has to be like that. You can have frameworks. Truss members can exist in things that aren't trusses. In frames that are not trusses. In frames that are not trusses. So for example, if I have a frame here, let's say I had a frame like this. This is definitely not a truss. I see a fixed support there, so automatically this thing is now no longer a truss. But I could have something like this. Fixed, 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 but this middle member here, this has pins on either end. And so as long as I didn't apply a load to the center of this thing, this thing here would be a truss member, and it would only carry one axial force. So as long as, again, as long as this thing had pins on both ends, so as long as anything, a member meets the truss assumptions, the truss conditions and assumptions, the truss member conditions and assumptions, it will have only a single axial force. Only a single axial force. Okay. And finally, I might want to look at truss determinacy. For a truss to be determinate. Truss determinacy very similar. You may remember the equation m plus r must be equal to 2j. Must be, I guess we could say less than or equal to 2j, but generally we say equal to 2j. And what this is, m again is the number of members, r is the number of reactions, and maybe I could put a number sign in there, number of reactions, and j is equal to the number of joints. J is equal to the number of joints. We know for a truss to be determinate, m plus r must be equal to 2j, But to be indeterminate, I also want to include this here. To be indeterminate, the number of joints, or the number of members plus the number of joints, would be greater than 2j. So if m plus r is greater than 2j, then your truss will be indeterminate. And the way this kind of makes sense is that if you think of a joint, if you think of doing equilibrium about a joint, the equations of equilibrium, you could have a sum of forces in the x direction and a sum of forces in the y direction. So essentially, each joint will give us two equations of equilibrium, a sum of forces in the x direction and a sum of forces in the y direction. We will not have a sum of moments about a joint because all of the forces coming into the joint will be have their lines of action well along the joint. So it would do no good to sum moments about the joint because they, again, because all forces go into the joint. And that's the basic idea of Truss determinacy. But again, so this represents our number of equations of equilibrium. While m and r represent unknowns. So m, of course, is the number of members, r is the number of external reactions, and so these represent unknowns. These are the things we would be solving for when using the method of joints. While j is the number of joints, and again, each joint is going to give us two equations of equilibrium. So if our m plus r is greater than 2j, that means that our number of unknowns is greater than our number of equations, and we know just from basic algebra that if our number of equations exceeds or is less than our number of unknowns, then we cannot solve it. Okay. And then next I'd like to look at truss stability, just like we explored briefly the frames before. Truss stability. So we can worry about internal versus external stability. External is going to be easy. Well, relatively easy. There's no formulas here. No formulas here to remember. For external stability, we are talking about whether the frame itself, that as a rigid body, is properly constrained. So actually, let's write external and internal. Keep these both in the same slide. External and internal. So the difference here, if you recall from earlier discussions, external versus internal stability would be, imagine if you have this truss floating in space. Will this truss be able to resist reactions? Will it have enough, external forces? Will there be enough restraint to keep this thing from moving around? It's that whole, if I pull it to the left, will it move? If I pull it to the right, will it move? If I move it up and if I pull it up and down, will it move? If I try to apply a moment to it, will it move? That's external stability. So the stability here is just your basic statics rigid body stability. So it's stable externally if there are at least three reactions. If there are at least three reactions, and two, these reactions that are not all concurrent or parallel. And we discussed this previously. So if you have a truss that has three roller supports, all of those would be parallel. If you had a truss that had three rollers that all of the lines of action coincided at a single point, that would not have moment stability about that point. Then we also have internal stability, and internal stability is discussing whether a truss is able to maintain its own geometry. So for example, if I have a truss like this, this would be a truss with an inbuilt collapse mechanism. So obviously this could not be stable. If I had something like this here, maybe a pin here, a roller here, and a pin here, this would be a truss that has an inbuilt collapse mechanism. Perfectly straight members here. Oh, there goes my truss. This has an inbuilt collapse mechanism. So that is obviously not going to be stable. For internal stability, truss must have no internal collapse mechanisms. No collapse mechanisms, and if M plus R is less than 2J, it's going to be unstable. And if M plus R is greater than or equal to 2J, it will be stable. So as long as the M plus R is at least equal to 2J, this thing will be stable. Again, as long as there are no inbuilt collapse mechanisms. But you may end up with you can very easily end up with a truss, if you're not careful, that is statically indeterminate, even though it is stable. It's just, we can't solve for all the forces, at least with only using the laws of statics, but that's the idea. Okay. Questions on that? Okay. Finally, I'd like to discuss the definition of a simple truss. I would like to discuss the definition of a simple truss. So simple trusses, this is a certain type of truss, or certain families of trusses. What is a simple truss? Well, fundamentally a simple truss is an idealized model, like all trusses are, but a simple truss is a truss that can be made by the following algorithm. Or process, or whatever you want to call it. One, start with a simple triangle. Start with a triangle. So you have joint, 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 member, member, member. And then two, add, repeatedly add, two members and one joint. So for example, I'll start with my triangle, and then I could repeatedly add two members and one joint. So if I add one joint and two members, it's still a simple truss. If I add a joint and two members, still a simple truss. If I add a joint and two members, still a simple truss. A joint and two members, still a simple truss. And let's discuss why is this significant. Well, if I look at my M plus R and 2J, all that sort of thing, here, if I look at M plus R and then 2J, M here is going to be 3. And let's say for simplicity that this had 3 reactions on it. Let's just say for simplicity this had 3 reactions on it. Maybe I have a pin here and a roller here or something. And then J, well, this would be 3 here. So in this case, M plus R would be 6, and 2J would be 6. So this would be the truest simple truss. In other words, it would be both stable because M plus R is greater than or equal to 2J, and it would also be statically determinate. So this is a case where, so the simplest case of trusses is where M plus R is equal to 2J. But then look what happens when I add a 2 members and 1 joint. 2 members, this adds 2 more unknowns. M goes up by 2, and J, the joint, M goes up by 2, and then the J goes up by 1. So as long as I keep adding 2 members in 1 joint, as long as I keep adding 2 members in 1 joint, M plus R will always be equal to 2J. keep adding two members and one joint, then m plus r will still equal 2j. And thus my truss will be both determinate and stable. And so that's sort of the friendliest type of truss. A nice, simple, the friendliest type of truss, it's stable, it's determinate. In other words, it's a simple truss. The name is very descriptive. Questions on my horrible handwriting? Okay. Someone looked a little confused. Okay. And that's the basic idea. Okay, questions on this? And also on simple trusses, any truss made out of a combination of simple trusses simply joined together, again with the m plus r equal 2j method, any trusses that are made like that, the whole thing will be a simple truss. So you can have trusses that are non-simple, especially ones that are, say, indeterminate, but that is the basic idea, and that is what I want to cover in terms of the theory of trusses. All right, that'll do it for today. Thank you for watching, and as always, thank you.